Dear students, today we continue our discussion of the probability distributions. In the last class, we have discussed normal distribution, and Z x minus mu by sigma. The corresponding sampling distribution was written as x bar normal with mu and sigma square by n. And the corresponding Z is x bar minus mu by sigma by root n. If x is normal with the mean mu and variance sigma square, Z is standard normal with the mean 0 and variance 1. In statistics, we come across squared quantities such as sample variance S square is equal to sigma x minus x bar square by n minus 1. In statistics, we come across squared quantities. An example is S square is equal to sigma x minus x bar square by n minus 1. To derive the sampling distribution of such squared quantities, we use chi-square distribution. Chi-square distribution. So chi-square distribution is used to derive the sampling distribution of squared quantities. Now, let us see what is a chi-square distribution. If x is normal with the mean mu and variance sigma square, Z is standard normal with the mean 0 and 1, then Z square is equal to x minus mu by sigma, the whole square, follows chi-square with 1 degree of freedom. So the square of a standard normal variable is distributed as a chi-square variable with 1 degree of freedom. With 1 degree of freedom. The concept of degrees of freedom will be discussed in detail in the next session. So, the definition is the square of a standard normal variable is chi-square with 1 degree of freedom. Now, we can generalize this. If Z1, Z2 and Zk, if Z1, Z2 and Zk are independently distributed chi-square variables, then the sum Z is equal to sigma Zi, I is equal to 1 to k, is distributed as a chi-square variable with k degree of freedom. If Z1, Z2, etc. Zk are independently distributed chi-square variables, then the sum sigma Zi follows chi-square with k degree of freedom. What I say is Z1, Z2 and Zk are independently distributed chi-square variables. Or if I say that if Z1, Z2, etc. Zk are standard normal variables, then the sum that is Z square equal to sigma Z I square follows chi-square with a k degree of freedom. You can read it, or you can read it as you like. If you read it as Z1, Z2 and Zk are independently distributed chi-square variables, the sum is sigma Zi, the sum sigma Zi chi-square with k. Or Z1, Z2, etc. Zk are standard normal, then sigma Zi square also follows chi-square with a k degree of freedom, where k means the number of independent terms in the sum. The number of independent terms in the sum. And here, as there are k independent chi-square variables, the degrees of freedom is k. As I told you earlier, I will consider the concept of degrees of freedom later in a different session. And we will consider different aspects of the concept of degrees of freedom. Anyway, so the sum of independently distributed chi-square variables, or if Z is standard normal, Z square is chi-square. So naturally, if Z1, Z2 and Zk, you keep it like this, are independently distributed standard normal variables, normal 0, 1, then Z square, that is the sum of, that is the squares of the sum of Z1, Z2, etc. Zk follows chi-square with the k degrees of freedom, where k is the number of terms or the number of independent terms in the sum. Now, if and this is the definition of chi-square. Now, if Z1, Z2, etc. Zk are independently distributed chi-square variables with the ki degrees of freedom, Z1, Z2, Zk are independently distributed chi-square variables with the ki degrees of freedom, then the sum sigma Zi also follows chi-square with the sigma ki degrees of freedom. If Z1, Z2, etc. Zk are independently distributed chi-square variables with the ki degrees of freedom, then sigma Zi also follows chi-square with the ki with the degrees of freedom is equal to sigma ki. If Z1, Z2, Zn are independently distributed random variables, each following chi-square distribution with the ki degrees of freedom, Z1 with the ki degree, Z2 with the ki degree, Zk with the ki degree, then sigma Zi follows chi-square with the sigma ki degrees of freedom. Or let us consider it simply as, if Z1 and Z2 are independently distributed chi-square variables, Z1 and Z2 are independently distributed chi-square variables, each with k1 and k2 degrees of freedom, Z1 with the k1 degree of freedom, Z2 with the k2. It means there are k1 random variables in Z1, k2 random variables in Z2. So the degrees of freedom k1 and k2. Then the sum, that is Z1 plus Z2. The sum Z1 plus Z2 also follows chi-square with k1 plus k2 degrees of freedom. So the sum follows chi-square with k1 plus k2 degrees of freedom. A simple case of this. And this property is known as the reproductive property. The reproductive property of chi-square distribution. This property is known as the reproductive property. So to summarize, if x is normal, z is standard normal. Z square is distributed as chi-square with 1 degree of freedom. And z1, z2, etc., zk, each following standard normal distribution, then the sum of squares of standard normal variables sigma zi square follows chi-square with a k degree of freedom. And if z1, z2 and zk are independently distributed chi-square variables with the ki degrees of freedom, that is ki chi-square variables in each, then sigma zi also follows chi-square with sigma ki degrees of freedom. And or if z1 and z2 are chi-square with k1 and k2 degrees of freedom, then z, the sum z1 plus z2 also follows chi-square with k1 plus k2 degrees of freedom. Now, if I expand this becomes z1 is this sum z is equal to x1 minus mu by sigma all square plus x2 minus mu by sigma all square plus etc. xk minus mu by sigma the whole square. So this quantity has k independently distributed chi-square variables. So this quantity has k degrees of freedom. Degrees of freedom will be discussed in detail. Now, the chi-square distribution, the PDF of the chi-square distribution is something like this. This is chi-square and this is f of chi-square. For chi-square distribution, the origin is 0. Chi-square, as it is a squared quantity, it will not take negative values. It will take only non-negative values. So it starts with 0. And for small degrees of freedom, it is highly skewed. So k is equal to 2. So k is equal to 5. K is equal to 5. But as degrees of freedom increases, it becomes more and more like a normal distribution. So degrees of freedom k is equal to 10. This is the shape of the chi-square distribution. And remember this, to find out the area property of chi-square distribution, you must always consider the degrees of freedom. And if you go through any book of statistics, you will see the tables providing areas of chi-square distribution for various degrees of freedom. You can refer any books on statistics and you will get these area properties. We will consider one case. Suppose that degrees of freedom is equal to 20. Then the chi-square distribution like this. Then probability that chi-square is greater than 10.85 is 95%. Probability that it is greater than 23.5 A3 is 25%. The probability that it is greater than 39.99 is 5%. In words, if degrees of freedom is 20, the probability of getting a chi-square variable in excess of 39.99 is only 5%. That means 95% of the area under chi-square will be between 0 and 39.99. You can calculate other areas for different degrees of freedom. Now, for the chi-square distribution, mean, that is expected value of chi-square, is k. Expected value of chi-square is k. That is degrees of freedom. And variance of chi-square is equal to 2k, where k is the degrees of freedom. Expected chi-square is k, and variance of chi-square is 2k. And chi-square distribution is extensively used for testing hypotheses about population variance. Testing hypotheses about population variance. It is also used for testing in the context of association between variables using contingency tables, that is test for independence, etc. We will consider such issues later. Anyway, chi-square distribution is skewed. Its mean is k, variance is 2k, and area properties depends on degrees of freedom. Now, as I told you earlier, we will not use estimators directly for hypothesis testing. We will not use estimators directly for hypothesis testing. For hypothesis testing, we develop test statistics based on estimators. As I told you, the test statistics based on x bar, that is z, is given as x bar minus mu by sigma by root n. Similarly, S square is the estimator of sigma square. But S square is not used directly for testing the significance of or making inference about the parameter sigma square. Using S square, we develop a test statistics. Now, the test statistics used for testing the significance of variance is given as n minus 1 into S square by sigma square. N minus 1 into S square by sigma square. And we can show that this quantity follows chi-square with n minus 1 degrees of freedom. That is, n minus 1 into S square by sigma square follows chi-square with n minus 1 degrees of freedom, where S square is an unbiased estimator of sigma square based on a sample of size n. S square is an unbiased estimator of sigma square based on a sample of size n minus 1 degrees of freedom. And if I expand this becomes n minus 1 into unbiased estimator of sigma square. S square is sigma x minus x bar square divided by n minus 1 divided by sigma square. That will give us sigma x minus x bar square by sigma square. So this quantity follows chi-square with n minus 1 degrees of freedom. And this quantity will be extensively used later to derive the t-distribution. So remember this, sigma x minus x bar square by sigma square follows chi-square with n minus 1 degrees of freedom. not a n degrees of freedom, even though there are n deviations here, n random variables here. There are n random variables, but all these variables are not independent. And the reason we will see later, that is why we have only n minus 1 degrees of freedom. So this quantity n minus 1 into s square by sigma square is used to test hypothesis about population variances. To test hypothesis about population variance, this quantity is extensively used. That is n minus 1 into s square by sigma square. So this is what is known as chi-square distribution. So chi-square distribution is nothing but the square of a standard normal distribution. And chi-square distribution is used to test the significance of population variance. So z square equal to x minus mu by sigma square follows chi-square with a 1 degree of freedom, and generalizing this sigma z I square, I is equal to 1 to k, follows chi-square with k degree of freedom, and a quantity which is used for testing hypothesis about population variance is n minus 1 into s square by sigma square, follows chi-square with n minus 1 degrees of freedom. N minus 1 degrees of freedom.